Example 1.2, given the signal x of t shown in figure 1.13a, 1.13, the continuous time signal x of t used in examples 1.21 to 1.13 a, x of t. Okay. The signal x of 3/2t correspond to a linear compression of x of t by factor of 2/3 as illustrated in figure 1.13d. In this d compressed here, this one here compressed, this one here 3/2 compressed 2/3. Okay. Here in between 2/3, here 1, 0 to 1, this d. Here the signal x of 3/2t corresponds 3/2t corresponds to a linear compression of x of t, linear compression. Okay, linear compression by a factor of 2/3. Okay, from 1 as illustrated in figure 1.13d. Specifically, we note that the value of x of t at t equal to t0 occurs in x of 3/2t at 3t equal to 2/3t naught. Specifically, we note that the value of x of t at t equal to 0, x of t equal to 0 happening occurs in x of 3/2t at 2/3. Yeah. Happening here, this one in 2/3. What is happening here? At t equal to 2/3t naught. This one. For example, the value of x of t, actually here in x of t, what is happening in x of that is x of t at t equal to t0 occurs in figure A. That one happening in t in compression, linear compression, x of 3/2t at t/23 t0. Here happening t equal to t0. Here happening t equal to 2/3 t0. For example, the value of x of t at t equal to 1 is found in x of 3/2t at 2/3. 2/3 equal to 2/3 of 1 equal to 2/3. Yeah, what is happening here in figure 1, this one happening in compression, linear compression here in figure D are happening under 2 by 3. Here 0 to 1, here 0 to 2 by 3. This time t, t equal to. So also since x of t is 0, x of t is 0 for t is less than 0. That is here already have seen in the last video. Here t is less than 0. From here this part t is less than 0. T is less than 0 since we also since x of t is 0 for t is less than 0. Yeah, here 0 no, this one 0. When t is less than 0, here x of t also 0. 0 we have x of 3 by 2 t is t0 for t is less than 0. Okay, also since x of t 0, okay, from x where is t is less than 0, full 0 only. We have x of 3 by 2 t 0 for t is less than 0. Similarly, since x of t is 0 for t by t is greater than 2, x of t is 0, t is greater than 2. X of 3 by 2t is 0 for x of t is greater than 4 by 3. Here in x of t, t is 0, t is greater than 2. That is this position. Here t is greater than 0, sorry, greater than 2, that time x of t is 0. Okay, like this here in figure for figure D, here happening after the 4 by 3, that is t is greater than 4 by 3, then x of 3 by 2 t is getting after that full 0 only. After that full 0. Okay, full 0. Okay, full 0. That's right. Figure 1.2, example 1.2 finished. Then 1.3, suppose that we would like to determine the effect of transforming the independent variable of a given signal. Suppose that we would like to determine the effect of transforming the independent variable of a given signal to obtain a signal of the form x of alpha t plus beta, where alpha and beta are given numbers. A systematic approach to doing this is first delay or advance x of t in accordance with the value of beta, and then to perform time scaling and or time reversal on the resulting signal in accordance with the value of alpha. The delayed or advanced signal is linearly stretched if alpha mod alpha is less than 1, linearly compressed if uh, mod alpha greater than 1, and reversed in time if alpha is less than 0. Yeah, yeah. Here, here it means here suppose that we would like to determine the effect of transforming the independent variable given signal x of t to obtain a signal of the form alpha x of alpha t plus beta, where alpha and beta are given numbers. A systematic approach to doing to this first delay or advance in x of t in accordance with the value of beta. Then to perform time scaling and or time reversal and the resulting signal accordance with the alpha. The delayed or advanced signal is linearly stretched if alpha is less than 1, linearly stretched, linearly compressed the time alpha is greater than 1, and reversed in time if alpha is less than 0. To illustrate this approach, let us show how x of 3 by 2 t plus 1 may be determined for the signal x of t shown in figure 1.13a. Since beta is equal to 1, we first advance shift to left x of t by 1 as shown in figure 1.13b. Since alpha is mod alpha is 3 by 2, we may linearly compress the shifted signal figure 1.13b by a factor of 2 by 3 to obtain the signal shown in figure 1.13e. That is, in 1.13a, to illustrate approach, let us show x of 3 by 2 t plus 1 may be determined for the signal x of t shown in figure a. X of 3 by 2 plus this one determined from here. This one x of t here x of 3 by 2 plus 1. This is in advanced happening. Here to illustrate the, let us show x of 3 by 2 t plus 1 may be determined for the signal x of t shown in figure 1.3a. Since beta is here is 1, we first advanced shift to left x of t, here shift to left from here compared to, okay, shift to left x of t by 1 as shown in figure b. Shift to left by 1 here, already we have seen here 1, this one distance, this one shifted here, this one here, this one shifted here. It means 1 shifted, okay, 1 shifted, one shifted left x of t beta equal to 1, we first advance shift to left to x of t by 1 as shown in figure 1.13b. okay, since mod alpha equal to 3 by 2, we may linearly compress the shifted signal figure, linearly shifted, linearly compressed, linearly compressed, linearly shifted. We may linearly compress shifted signal figure B. Linearly compressed and shifted this one from this figure A. Okay. Here also 0 1 0 1 same, but shifted left. That's all. Compress shifted in figure B by a factor 2 by 3 to obtain here in E linearly shifted and compressed, both here happened here by 2 by 3, but here linearly shifted only, left, that is advanced here, okay. In addition to their use in representing physical phenomena such as the time shift in a sonar signal, and represent speeding up reversal of audio tape transformation of the